Okay, everybody, welcome to this week's ISGC seminar. Today's speaker is Valerio Bozza. He did his PhD in 2002 at the University of Salerno, where he is now an associate professor. Thank you, Valerio, for agreeing to give this talk, and the stage is yours.
Okay, thank you very much for this invitation. So it's my first time in this series of intercontinental seminars on gravity and cosmology. It looks like a very interesting series, and I enjoyed looking at all videos on YouTube that you uploaded on YouTube. So I hope to do my best to keep the trace. Okay, in this talk I will speak about gravitational lensing by black holes, and you can see in the title slide you can see this picture taken from the Interstellar movie, and we will speak about Interstellar later on during this seminar. I will mostly focus on analytical results. So what can be analytically found from the physics of gravitational lensing around by black holes using general relativity, and how these analytical results can be informative of the physics that we find around black holes. So I will start from by an overview of gravitational lensing in the strong deflection limit. So I will start with the analytical results that can be obtained using keeping the spherical symmetric of the problem, and then we will move to to Kerr metric. And of course, this is more physical, but of course it's also more difficult from the mathematical point of view. After this first part of the seminar dedicated to analytical results, we will move to observations. So we will try to find cases in which we can apply this analytical formula. And of course, we will speak about Sagittarius star, which is a natural laboratory for gravitational lensing. And in the end, of course, we will also cover the black hole imaging by interferometry, so event horizon telescope results and and similar. Okay, so let's start from the very beginning. So we know that the gravitational lensing was just a prediction by general relativity. So Einstein himself found the famous formula for the deflection angle by Schwarzschild lens. And in this case, he just took the weak field limit. So he integrated the null geodesics in Schwarzschild. And in the end, since the integral was very difficult, he just made the weak field limit, and he found the classical formula that we find everywhere in textbooks about general relativity. Indeed, it was soon realized by Eddington, actually, that there is a secondary image appearing on the other side. So if we have a typical gravitational lensing problem in which we are an observer here, a gravitational lens somewhere in the middle, and the source behind the gravitational lens, the light can take two different paths to reach the observer. So in general, we have a primary image and a secondary image. And this is more or less the phenomenology we have in gravitational lensing if we stay in the weak deflection limit regime. But actually, we can try to go beyond the weak deflection limit. After all, the general relativity gives us this integral in Schwarzschild metric, and we can try to make a bit better than the weak deflection limit. And indeed, this was done by Charles Galton Darwin in 1959. So he managed to solve the integral in terms of elliptic integral. So this f here is an elliptic integral of the first kind. So the formula looks quite more complicated, but after all, it's still something that you can write analytically in some way. So if we make a plot of this deflection angle without the weak deflection limit, we have this solid curve here. So indeed, if the impact parameter is very large, so compared to the Schwarzschild radius, we go back to the weak deflection limit, and so we recover Einstein's formula for the weak deflection limit here on the right of this plot. And indeed, you can see the comparison between the exact formula and the weak deflection limit, which is the dotted one, and they practically coincide at the large impact parameters. But if we go close to the black hole, if the impact parameter is small, at some point we find that that a discrepancy between the exact formula and the weak deflection limit, and we have a divergence. Even have a divergence at a finite value of the impact parameter. So we have no gravitational lensing if the impact parameter is smaller than this minimum value. This minimum value can be calculated very easily, actually, and it's just 3 times the square root of 3m, as it is stated here. In principle, it is possible to make an expansion of the exact formula that we see on the left close to the divergence. And this was done by Darwin himself, who proposed this strong deflection limit formula, which shows that this divergence here, the deflection angle, is a logarithmic divergence. So it can be put in this form. So if we close to this minimum value, we have this logarithmic divergence. What does this mean, actually? The deflection angle becoming higher and higher? Well, it means that the light rays will make more than one turn around the black hole. So this means that at some point we will have a deflection angle of 2 pi, which corresponds to a complete loop around the black hole of the photon. And in fact, this is what if we go from the weak deflection limit to the strong deflection limit, this is what we see. So this is the trajectory we would have for the light ray in the weak deflection limit. So just a small deflection like that, and so we are in the Einstein's formula regime. But if we have a smaller impact parameter, the deflection angle will increase, and if we make the light ray passing closer and closer to the black hole. Actually, what happens is that the deflection angle will reach 90 degrees. At some point, it will reach 180 degrees. So the light ray will go back towards the observer. So this is also called retrolensing sometimes, this regime. And of course, you can also have a light ray that make one complete turn around the black hole and then reaches the observer. Which means that the observer will actually see another image besides the weak deflection limit image that we found in the first place. We have another image which is made up of photons that make one complete turn around the black hole and then reach the observer. And of course, since there is the divergence, you can also have particular impact parameters for which you have a deflection angle of 720 degrees and so on and so forth. So indeed, what you see is an infinite sequence of images of the same source. At some point, if the impact parameter is exactly this value, so the minimum impact parameter value, the light ray is just injected on a trajectory, on a circular trajectory around the black hole. And of course, if the impact parameter is smaller than actually the light ray has no way to get out of the gravitational field of the black hole, so it will be destined to fall inside the event horizon, and it will be just eaten by the black hole. So there is no gravitational lensing anymore. Of course, all these pictures can be reversed, which means that actually, if we are a distant observer, we will not see any light rays coming from inside this impact parameter, this minimum impact parameter. So if we are an observer here in this picture, this green point here, all stars in the universe will actually generate images that will appear at impact parameters larger than this minimum impact parameter If we are an observer at a distance r0, which this means that we will see a black spot on the sky with a radius theta m equal over r0. And this is the famous shadow of the black hole. So all images of distant stars will appear outside this shadow, and this shadow will appear completely black. On the left here, you can see another picture from a Luminous paper in 1979, in which he just illuminated a black hole, and then you have a return of light from the light rays that are backscattered by the black hole. So the black hole will respond to a flash of light with a ring just outside the shadow of the black hole. Okay, so apart from the shadow, from the black shadow of the black hole, we have stated before that actually we see an infinite sequence of images, because we have light rays performing one complete loop around black hole, light rays performing two loops around black holes, and these light rays will form different images. So indeed, if we have a source somewhere behind the black hole, we will see an infinite sequence of images on one side. But of course, light rays can also take the other way around the black hole, and they will form another infinite sequence of images on the other sides. And these images will be images with negative parity. So we have an infinite sequence of images on one side with positive parity, and an infinite sequence of images on the other side with negative parity. And all these results were actually already contained in Darwin's paper in 1959. So this is the phenomenology we see around the Schwarzschild black hole. But actually, this logarithmic divergence is not specific of Schwarzschild, but it is actually universal, which means that you can find it in whatever metric of black holes in sharing the same properties of Schwarzschild. And this was shown by myself in 2002, actually. So if we consider a generic spherically symmetric metric like this, with generic coefficients AR, BR, CR, describing this space-time, we can easily find the condition for the formation of an unstable circular orbit, because we can write down the geodesic equations. We can find the equation for the radial coordinate, and we can just impose that r dot is equal to 0 and r double dot is equal to 0. So if we make this calculation, that we find a condition on the coefficients. So the position of the unstable circular orbit is just given by this simple equation involving only the coefficients c and a. So it's a very simple equation. It was also it was found several times. So for example, you can find it in this paper by Claudel, Wilbert, and Ellis of 2001. And this radius is also called the radius of the photon sphere, because in principle, photons can perform the circular orbit with this radius with whatever orientation, because of the spherical symmetry. So in practice, all the sphere with the radius will be populated by photons, winding around black holes on this circular orbit. Of course, this orbit is unstable, which means that with a small perturbation, actually, the photon will leave the orbit, it will escape to infinity, and this is the case of gravitational lensing. Or if the perturbation is in the other way, the photon will just fall, spiral, and then fall in the black hole. Okay, so actually, we can also try to understand whether the formation of an unstable circular orbit is a generic outcome of spherically symmetric metrics. And indeed, if we impose that the metric is asymptotically flat, and we also impose the existence of a horizon, which in this case is just equivalent to the condition that A of R vanish somewhere, and so at the vanishing point we will find the horizon. So these two conditions alone are sufficient to have at least one photon sphere. Of course, you can think about crazy metrics in which you have more than one photosphere. This is possible. This has been shown that it has been possible. I don't remember the explicit example, but I think you can find it somewhere in the review by Perlik and Supko. Okay, so indeed, once you find the existence of this unstable circular orbit, just by finding the root of this equation, which we call Rm, we can immediately find the radius of the shadow, because you can easily find the impact parameter for the photon coming from infinity and reaching this unstable circular orbit, which is just found by geodesics equation. So this formula is just this. So UM is just given by the square root of CM over AM. So once you find Rm, you put it in C and A, and you obtain this formula here. So CM means the function C evaluated in Rm. So this is a short notation for saying that this is the same function C appearing here, evaluated at R equal Rm, the radius of the stable circular orbit. So we have the simple formula for the minimal impact parameter. Of course, the radius of the shadow depends on the distance of the observer. So it will just be the angular radius of the shadow will be the minimal impact parameter divided by the distance of the observer from the black hole. And so in a very few steps, you can find the angular radius of the shadow for whatever metric you like. Okay, so so far this is for the shadow, but we want to describe gravitational lensing. So the formation of images of these higher order images formed by photons performing one or more loops around black holes. So in order to describe these images, we have to go very, very close to the shadow. So we can just write down the position of the image theta as the angular radius of the shadows multiplied by 1 plus epsilon, where epsilon is very, very small because we want images appearing just outside the shadow. And so we can see what we can get if we expand our formula in terms of this epsilon. So if this epsilon is very small, actually everything can be done more or less analytically. And indeed, you can solve the integral describing the trajectory of the photon, and you can find that the azimuthal variation, that is the deflection angle in some way because the deflection angle would just be this azimuthal variation minus pi, because pi is just the azimuthal variation of a photon along a straight trajectory. And this formula, in this formula, you can see that actually you can find the logarithmic divergence in terms of epsilon. So indeed, whatever the metric, space-time metric you have, you will always find, if you have a photosphere, you will have a logarithmic divergence of the deflection angle of trajectories coming very close to the to the shadow. And these eta O and eta S are just a function of the observer and source positions. So eta O, as you can see here, is just 1 minus Rm over Ro, and eta S is the same. So for very distant observer, eta O is equal to 1, and for the very distant sources, eta S is equal to 1. So they disappear from the equation, basically. And these two coefficients, A and B, these are specific of the metric of the space-time metric you are considering. So indeed, they can be put in terms of functions of the metric. So you can find again A, B, the same coefficients we had for the space-time metric here, evaluated at the minimum at the unstable circular orbit Rm. And as you can see, the coefficient of the logarithmic divergence only depends on the values of these functions taken at the photosphere. So A is actually completely determined by the local geometry at the photosphere. On the other hand, the other term, the constant term here, depends on the full trajectory of the photon. So is obtained, as you can see here, from an integral along the whole trajectory of all the functions of the matrix. So it's more complicated. So indeed, it can be obtained analytically in a very few cases. For example, in Schwarzschild, it can be found analytically. But in general, this integral can only be evaluated numerically. Of course, if you consider small perturbation of Schwarzschild, you can find you can also write down an expansion of this integral in terms of your perturbative parameters. So some analytical results can also be obtained for many cases. Okay, so as you can see, after all the calculation of the deflection angle in the strong deflection limit can be put on one single slide. So after all, it's not so difficult to calculate it for whatever metric you want. And indeed, after my work in 2002, many people have tried to calculate the deflection angle in whatever metric, and so they found many results on metrics with complicated theories of gravity and whatever they like. Okay, so once we have the deflection angle, we still have to describe the images, but that's very easy because after all, we should just invert this formula for the azimuthal variation in terms of epsilon. And then you get the epsilon at which you will see the images. So if you have a source at some position phi s, at some azimuthal position phi s, this is the formula. This is the formula describing the position of the images. And indeed, here you can see it at 2n pi, because of course the position of the images, the image depends on how many loops you are considering around the black hole. And if you take n to infinity, of course, this exponential will go to 0. So which means that an image formed by photons performing infinite number of loops will actually appear exactly at the shadow boundary. Why? If you just consider one loop, then you have the outermost image of this infinite sequence, which will be the most prominent one. Okay, so after all, the position of the images follows this exponential formula. So this infinite sequence of images is actually exponentially packed toward the shadow boundary. Yeah, well, we can plot these positions on as a function, for example, of the delta phi of the azimuthal variation. And for example, delta phi equal to pi corresponds to a source behind the black hole in which you have two images. So this will be the weak deflection limit images, the outermost image appearing here, and then this will be the two images formed by photons performing one loop. These are the two images for the photons performing two loops, and so on. And if you move the source on the other side, so from pi to 0, then you have the retrolensing situation on the other side. An important thing about this formula is that they continue to hold for sources inside the photon sphere, because of course, if we speak about lensing, we always have in mind the situation in which we have a distant source and a distant observer. But actually, this formula hold even in the case in which the source is very close to the black hole, because the source distance enters through this eta s. And if the source is inside the photosphere, so inside the circular orbit, what happens is that its eta s is negative. And if eta s is negative, of course, for consistency, epsilon must be negative here. Which means that actually the images, the gravitational lensing images for a source inside the photosphere will appear close to the shadowy boundary, but from the inside, not from the outside. And you can plot the logarithm of minus epsilon in this case, and you have a similar plot for this situation. But actually, these images will be on inside the shadow boundary, very close to the shadow boundary. Another important fact is the extension, so the magnification of these images, because as you can imagine, since these images are exponentially packed towards the boundary, their extension is exponentially depressed. So these images are extremely faint because they are extremely small. They cover an extremely small area in the sky. Actually, the tangential extension must be the same as the tangential extension of the source. This is just by spherical symmetry. But the radial extension picks up this epsilon here, which is an exponential. So indeed, the radial extension is exponentially suppressed. So if you start with a generic source with some extension delta theta 0, actually which is given by some formula, actually the total area covered in the sky by this image will become exponentially small. So this is a plot of the magnification as a function of delta phi. So here from 0 to pi we will have the primary order in the weak deflection limit. This will be the secondary image, which is in the weak deflection only here, and then it goes to the strong deflection limit here. And then you see this regular exponential decay because of this epsilon term here. So the strong deflection limit works from, let's say, 2 pi on, and then you have this exponential decay, which is reproduced by this plot here. Okay, another thing we can do with the spherical symmetric metric, we can try to complicate the problem a little bit, because indeed, up to now we have spoken about null geodesics, so we were speaking about light rays traveling in vacuum. But actually, the space around a black hole is not vacuum. We have, in particular, we may have plasma, and as we know, plasma can induce refraction, conventional refraction. Electromagnetic waves are refracted by plasma, and so we can take this into account. So there are several papers, in particular by Bisno Matikogan, Adam Rogers, Oleg Tsupko, describing plasma, gravitational lensing by black holes surrounded by plasma. And what you have to calculate is the plasma frequency, because the refraction index depends on the plasma frequency, omega e here. And omega e, this plasma frequency, is a function of the density. It just depends on the density of plasma you have around the black hole. But actually, the gravitational lensing problem doesn't become too difficult, because it is true that we have gravity and electromagnetic effects altogether. But actually, if you write down the equations, everything works the same, with just the replacement of a, or the function a that we found before, with a new function, which is just an effective coefficient, which is just a multiplied by the refraction index to the power -2. So you can recover all the previous results. So everything works the same, actually, and you can immediately calculate the new photon sphere, for example, taking into account the effect of plasma and gravitational lensing in the presence of plasma. So this is something that we did in a very recent paper. So after all, in only this year it was published with Oleg Tsupko, who is an expert of gravitational lensing of plasma, with my PhD student Fabiano Felippa. And you can see that indeed, depending on the power law that you choose for the density of the plasma, you can have different gravitational lensing, different deflection angles. So these are different deflection angles that you obtain with different powers of this power law. So it's possible to describe also this effect and to recover this effect in the formalism developed up to now. Okay, now let's move to Kerr. Of course, we know that the real black holes are not spherically symmetric. So indeed, if we want to make contact with real black holes, sooner or later we have to abandon the spherical symmetry. Kerr geodesic, you can find them whatever textbooks, for example, the mathematical theory of black holes by Chandrasekhar, for example. And indeed, Kerr geodesics can be put in integral form thanks to Carter. So we know Carter introduced this Carter's constant here, Q, and everything can be put in terms of these first order integrals. And you can also explicitly write down these geodesics in terms of elliptic integrals. This was done by Rauch and Blandorf in 1994, but you can find them in many, many papers, actually. And indeed, you can find a lot of numerical or semi-analytical codes solving Kerr geodesics and performing ray tracing around Kerr black holes. Of course, it's difficult to have a code that is fully stable if you want to investigate light rays performing several loops around black holes, because in that case the stability of a numerical black hole becomes very complicated. But indeed, if you want to have a picture of the appearance of a black hole, these codes are very, very good. But we want to find some analytical results also in the kinematic. And what first question is what changes if we go from Schwarzschild to Kerr black holes? What happens to our higher order images that we calculated in the Schwarzschild black hole? What happens to caustics? And what can we get from these analytical approximations? And it is the first thing we can see is that the shadow of the black hole changes, because of course Here is another picture from the review by Perlik and Supko, which is very, very good, and so I suggest people to read it. And what you can see is that the shadow of the black hole becomes asymmetric. Of course, if you have a light rays that co-rotate with the black hole, so the black hole here is rotating around its spin, so light rays co-rotating with the black hole are allowed to go closer to the horizon, and so the shadow will actually become smaller on this side, while light rays counter-rotating will have to stay far away from the black hole because otherwise they will fall into the black hole. So on the other side, actually, the shadow becomes more extended. So this shadow becomes asymmetric, and you can plot the shadow as a function of the spin parameter of the black hole, and you can see that the shadow moves to the right and becomes elliptic, and it also flattens on the on the side of the co-rotating black hole, or the co-rotating photons. Apart from these results on the shadow, which are known since many years, we found very strange that nobody has ever calculated the perturbations of images for low spins. So actually, higher order images in Kerr black holes can be calculated numerically with those retracing codes, but it is still possible to derive some analytical results about the position of images if we consider a Kerr black hole with very low spin. So if we start from Schwarzschild and we make an expansion for low speeds. And a few months ago, we published this paper with Fabio Ratore, another PhD student of mine, and we found that what happens is that higher order images rotate, change their position angle, so they rotate around the shadow of the black hole. So in this picture here, you can see the image n equal 1, so one loop around the black hole, n equal to 2 loops around the black hole, 3 loops around the black hole, and you can see that their position angle changes. So instead of being all images aligned along the same line, as in the Schwarzschild black hole, in which you have a spherical symmetry, images appear around the black hole at different position angle, and this perturbation of the position angle can be written down in a very simple formula here. After all, this formula only depends on the zero-order position angle alpha 0, the source position, of course, through mu s and alpha s, the observer viewing angle, mu o, so if the observer is on the pole of the spin of the Kerr black hole or on the equator, and the Schwarzschild deflection psi tilde. So after all, everything depends on very few parameters. You can find this perturbation of this position angle. Also, the distance of each image from the shadow changes. So also epsilon, this distance from the shadow, changes according to this formula here. So you can write down a simple analytical formula also for the distance from the shadow. You can make plots, and indeed, this is a plot of the position angle, and you can see that if you have alpha 0 is the position angle in the case of in the Schwarzschild case, and then if you turn on the spin, then you have this position angle is perturbation of the position angle, which is changing. And you can also see that the images on the poles of the Kerr black hole are the ones that are mostly shifted by by the spin of the black hole. And this is for the positive parity images and for the negative parity images. This is the plot for the epsilon, for the distance from the shadow, and you can find that the effect changes sign depending on the position of the source, which means that actually co-rotating photons appear closer, and counter-rotating photons appear far away from the shadow, and this is tracked by this epsilon appearing here. This is for the positive parity image, and this is for the negative parity images. So it's funny that these simple results has only been derived very, very lately. Now, apart from these perturbative pictures, so what happens if we have a low spin? An important difference between the Schwarzschild black hole and the Kerr black hole is the presence of extended caustics. In the case of the Schwarzschild black hole, actually we have 1 point caustic because in order to have a diverging magnification, you have to put the source exactly on the optical axis. While in the case of spinning black hole, we have a different situation. Indeed, in Schwarzschild, if we have a source here, we have the two infinite sequences of images here. But in order to have an infinite magnification, we have to put the source very close to the optical axis. And so you have the same caustic point for all images of every order. So for the weak deflection, for the strong deflection image at order 1, 2, and so on and so forth. The caustic point is the same for all images because of the spherical symmetry. In the case of spinning black hole instead, you have different caustics for different orders, which means that we have a first caustic for for the weak deflection limit images, for the primary and secondary images. And so if you put the source close to these caustics, only these two images will brighten, while all other images will stay faint. We have a caustic for the for the first order higher order images, and so if you put the source close to this caustic, actually the first order image will become bright, while the weak deflection limit will stay faint. And so on and so forth. If you put the source close to the second order caustic, the second order images will become brighter, and so on and so forth. So the caustics do not coincide, but as you can see from this plot, actually caustics also become extended, which means that these caustics will have this classical asteroid shape, which has been described in the weak deflection limit in this paper by Mauro Sereno and Fabiano De Luca, and in the strong deflection limit in some papers of mine. So actually the radius of this caustic can also be calculated analytically in the limit to second order in spin. And an important fact is that you can have additional images appearing because, of course, if you have a source inside the caustic, two additional images will appear. And indeed, this means that the number of images can become very, very large in the case of Kerr caustics. Oh, this result here is a similar result that we derived in the case of a Schwarzschild black hole perturbed by external shear. Also, in this case, it's possible to find extended caustics. Now, if we want to plot caustics, actually caustics depend on the distance, on the source distance. So you can plot this asteroid shape in 3 dimensions, and that will become surfaces depending on the source distances. So this is the picture for the first caustic, the caustic in the weak deflection limit, and Racco and Blandford showed that actually this caustic will wind around the black hole for sources very close to the black hole. In another paper in 2008, actually, I showed that higher order caustics can become very, very large. And in the limit of extreme Kerr black holes, they will even wind more than wind around black holes. And so they will self-intersect several times, which means that actually the generation of images in this case will lead to a number of images that will grow exponentially large. So instead of having only a pair of images of order m, actually we will have more and more images, and the number of images will increase exponentially with the order m, because these caustics will be self-intersect many, many times. Now, there is an unexpected spin-off of this paper in 2008, and then this goes back to the picture in the first slide about the interstellar movie, because if maybe some of you know that the picture of the black hole in interstellar movie was realized by assistance of Kip Thorne, which is of course was the maximal expert of general relativity. So Christopher Nolan asked Kip Thorne to make the black hole as realistic as possible, and indeed it is funny that in this paper in which Kip Thorne described how the pictures of the black hole were realized, he also mentioned the paper by Racco and blunt for this, and also this paper about caustics in curved black holes. So indeed, these theoretical studies about gravitational lensing at least are useful for science fiction movies. At least we have a spin-off in science fiction movies. Okay, apart from this funny result, let's go to the observation in the last part of this seminar. And so, where we can actually see this gravitational lensing by black holes at work, apart from science fiction movies. And we know that we have supermassive black holes. We have a supermassive black hole in the center of our galaxy, the famous Sagittarius A star source, which has been detected in the radio band in the first place, and it was also detected in the near infrared and in the X-rays. So this is the picture in the near infrared, and it has been studied in several bands. Now I will go back to radio band later. Let's concentrate on the near infrared, and there is a series of papers describing gravitational lensing by Sagittarius star, and they date back more than 30 years, more than 30 years. So there are several effects related to gravitational lensing by this black hole in the center of the galaxy. We should see a slight depletion in the central region. Some stars should have a secondary image that should be detectable. We should have a shift of the primary image of stars close to the central black hole. And of course, we have some ideal sources, which are the stars in the central clusters. There are these S stars that orbit the central black hole, and of course, we know that they are monitored by many big telescopes that look for the effects of this central black hole that can be tracked by the study of the orbits of the stars. And for many of the stars, now we know the orbit very well. We know the orbital elements, and in particular for S2, we know that also the relativistic precession has been measured, and we know the famous paper, the result of the precession of 12 arc-minutes per orbit, which is a striking confirmation of a general relativity leading to a Nobel Prize. And also these measurements have led to the most accurate measurement for the mass of the black hole. So what can we do with these stars? Of course, we need exquisite astrometry, because it's not easy to show these gravitational lensing effects for these stars, because they have not a perfect alignment around the black hole. So we have to find a very, very elusive astrometric shifts of the stars due to gravitational lensing, and this could be within reach of the gravity instrument, performing interferometry with at the VLT. And indeed, in this study with Luigi Mancini in 2012, we calculated the astrometric shift of the images of the S stars, and we found that many of them should be within reach of the gravity instrument, with a shift higher than 10 microarc seconds. And of course, this will be a very interesting fact, because we could study gravitational lensing by the black hole, derive an independent measurement of its mass, test for possible post-Newtonian effects, and also spin effects. Another thing that we've done recently with another PhD student, Silvia Petroni, is the impact of the gravitational lensing in the reconstruction of the orbital elements of the S stars. And we found that actually already with the current data, we are marginally sensitive to lensing effects. So we advocate for the fact that the lensing effect should be included in the fit for the orbital elements of these S stars in order to calculate the accurate orbital elements. Now, looking towards the future around Sagittarius star, there are very good perspectives from the survey that the Roman Space Telescope will take starting from 2026. This space telescope will perform a survey of the galactic the bulge regions in search for planets, for extrasolar planets through the microlensing effect. But very recently, actually, in this white paper by Sean Terry and other people, it was requested, a survey of the galactic center was requested with this telescope. And indeed, we will have a high cadence monitoring of stars around the Sagittarius A star. And of course, it will be very precious to understand the motion of stars around Sagittarius A star and to find any effects that could be related to general relativistic effects in the motions and also by effects due to gravitational lensing of these stars. So we will be very curious to see if we will detect anything with this stuff. Now, in the very few minutes that are left, we will speak about Event Horizon Telescope, because now we have the ability to see black holes in detail, and this is indeed a breakthrough for the field of gravitational lensing by black holes. Now we have the results about M87 star, the black hole in the galaxy M87, and the black hole in Sagittarius A star. But the problem of Sagittarius A star is that it has a variability of the order of minutes. So it's difficult to take pictures of Sagittarius A star black hole because it varies so rapidly. While the results for M87 are much more solid, and so we can try to find even fine details in the image of M87 stars, which would be inaccessible in the case of Sagittarius A star. Of course, we know the story. So there are these 8 radio telescopes scattered all around the Earth's surface. So in practice, by combining the signals recorded by this radio telescope, we can probe the so-called complex visibility function in the angular frequency space. So these UV are the angular frequencies, and so all these colored tracks are the points in this space that are probed by pairing these radio telescopes. And indeed, we can go to angular frequencies equivalent to a resolution of 25 microarc seconds. Of course, we know that it is not the same as a real image because it is a sampling in the visibility in the angular frequency space. So we need to couple this data with a model, with a theoretical model of the black hole in order to have a picture like this. Otherwise, we should just see these amplitudes in this space, which is a different thing. Anyway, this picture that has been reconstructed by the Event Horizon Telescope collaboration is actually the blurred image that has been generated by considering a resolution 25 microarc seconds. But the model images are actually this. So should contain much more details that are still inaccessible to us. And in these images, we can easily detect here this photon ring, which is actually the ring surrounding what we called the shadow of the black hole. But inside what we call the shadow of the black hole, actually we still have an accretion flow extending down to the horizon of the black hole. And so the black spot is actually corresponding to the so-called inner shadow, which is not the image of the photon sphere. It is actually the image of the horizon of the black hole, because we should also take into account the matter that is already inside the unstable circular orbit. That's why we have some white spot also here inside the photon ring. But indeed, this photon ring is created by higher order images of this accretion flow. And okay, here you can see that actually the word shadow is being replaced by critical core, but I don't like critical core either because it's a different mathematical concept. So I would prefer to stick with the old word shadow. Okay, if we look at the photon ring, actually we can see that there is a structure, because we have seven images of order 1, 2, 3. We will actually generate a sequence of rings, one inside the other. And in this very famous paper by Johnson et al. Appeared on Science, you can see that if we had enough baseline between the radio telescope, we could distinguish these different rings. And we can, going to a baseline of the order, order of or geocentric orbit, we would see the ring of order 1. But with the radio telescope on the moon, we could see the ring n equal 2. And at point L2, the Lagrangian point L2, we could even see the ring of order n equal 3. So in principle, we are able to access these higher order images that we're just seen in the science fiction movies so far. So this is indeed a very interesting perspective. And now my time is running up, so I'll go very fast on the last few slides. So we also decided to consider the images of a compact source around a spherically symmetric black hole, and we tried to derive the complex visibility function analytically. This is indeed feasible. So using the same formula we had before, we described the images of a compact source around a black hole in the real space. And so if we take a Gaussian profile just as a model for the source that is being imaged by the black hole, we can easily calculate the Fourier transform of this the image in the real space, and we get the complex visibility. And everything can be done analytically indeed. And of course, the complex visibility is just a sequence of Gaussian steps with a phase factor. So this would be the complex visibility in the UV space. But of course, if we take just a slice on the U space, we get the complex visibility like this as a sequence of steps. Now, the shape of these steps will depend on the position of the source, if it is behind the black hole, on the side of the black hole. So this is at 90 degrees, and these are the same plots, the plots with different extensions of the source, and this is the plot with different positions of the sources. So, but everything can be tracked analytically by this formula that you see on top of this slide. Once you have this complex visibility in an analytical form, you can also try to invert it to find, for example, the coefficient of the logarithmic divergence by taking the ratios of the heights of the two consecutive steps, which this is only determined by the coefficient of the logarithmic divergence. The source position is given by this formula, the radius of the shadow by this formula, and the constant term of the deflection angle by this complicated formula, depending on the periodicities of the oscillations that we have seen. Of course, we have also extended the study to generic spherically symmetric metrics using the same formalism that we developed so far, so you can calculate it for Reissner, Nostrom, or whatever you like. And as we can see, of course, we can confirm all the results of Johnson et al. Paper. And I want to mention that there are current debates about the extension of the Event Horizon Telescope with orbiting radio telescope. So this is the so-called Event Horizon Explorer. So this is a project of radio telescopes orbiting the Earth. But of course, once this works, we can also put a radio telescope on the moon in L2. And so we can actually try to probe these steps in this complex visibility function. Okay, in the infrared, actually the perspectives are more complicated. In principle, we gain a factor 100 in resolution, but actually the stability of the configuration of the satellites operating in the infrared is much more complicated than in the radio band. So this is a futuristic project, this LIFE project, that is being designed for imaging terrestrial exoplanets, but it will also be useful for this kind of study of gravitational lensing by black holes. And okay, so I made up to the conclusions. So in conclusion, we can say that there is a long tradition of studies about black hole gravitational lensing. And of course, we are very interested in these studies because this provides access to space-time matrices in the strong field regime and potential tests of general relativity or other theories of gravitation. Of course, most of the attention is on Sagittarius A star, which is the closest supermassive black hole that you can see in some detail. But of course, also black hole imaging is very, very promising because it probably provides access to these higher order images in not so many years. So this sending a radio telescope to space is not extremely complicated. Of course, there is a payload which is very heavy. You have to ensure stability of of the signal between the telescope and the Earth. There are some technological challenges, but it's not so complicated. So I think that in the next decade we will probably see these higher order images for the first time. Okay, and that's all for my talk.
Thank you, Valerio, for this nice talk. Are there any questions?
I have two questions, if I may.
Yeah.
Please feel free.
One is I've been looking at these papers. I haven't tracked through all the details, but they say that there's a relationship between the kind of behavior of photons near the photon ring and the quasi-normal modes. Is that?
Yeah. Yes.
Yeah,
Yes.
I wonder if you can comment on this, and also not just the theoretical part, also observationally, because you did spend some time talking about observations, whether these two things are in fact complementary. If I study, let's say I do gravitational waves and I detect these, ring down and quasi-normal modes, is that really a complementary observation to studying, these lensing effects around black holes? Could you comment on that?
Yes. Indeed, both phenomena rely on the same physics because these quasi-normal modes depend on the propagation around this unstable circular orbit. That's why you find exactly the same physics. So indeed, this quasi-normal mode give information on this on the coefficient of the logarithmic divergence because they are related to the same physics, the propagation of a wave on this unstable circular orbit. So there is a strong relation between the two phenomena, and indeed, I've never investigated the quasi-normal modes myself. I know about this relation, which has been invoked many times, but I've never studied myself gravitational wave ring down. But I think that indeed these two studies are related. I don't know if also the constant term enters somewhere in the quasi-normal mode. So maybe you have looked at those papers recently. I looked at them many years ago, and I don't remember if there is a relation also involving the constant term in the deflection angle, because that term depends on the full trajectory of the photons from the observer to the unstable circular orbit. So it's more involved, but. Indeed, it will be interesting to relate these two studies with recent data.
I see. And presumably it does depend on being the metric described by GR as well. Is that right? Because what I mean is that, people are interested in modified gravity, and if somehow we look at gravitational wave observations and compare them to lensing observations, and somehow or other they don't, if they don't match up, then the way we expect it to, right? Then would you say that that might be an alternate test, a new test of GR in that sense?
Wow, that could be very interesting. Actually, if I stick to geodesics, I would say there shouldn't be any differences in whatever theory of gravity. Okay, because if you study the propagation along this unstable circular orbit, then you are actually looking at exactly at the same phenomenon in the two cases, so in gravitational lensing and in gravitational waves. If you find any differences, that would be very striking because indeed, in one case you have gravitational waves, in one case you have light rays, and if you find any differences, that would be very crazy because you would say, okay, gravitational waves propagating differently from photons, and then that would be really incredible.
Because in one case, it just depends on the Maxwell's equations on some fixed metric. but in the other case, you have perturbed your gravitational equations, right? And if somehow or other it turns out not to be GR, then it would give you a difference, I would imagine. Yeah.
Yes, yes. Then that would be very interesting indeed. Yeah.
My second question is related to just a theoretical study of geodesics themselves. I remember also, I think it's Gary Gibbons and his collaborators using these Gauss-Bonnet theorems to.
Yeah.
I wonder if that also applies for these things that go round and round many times. Is it applicable also, or have you thought about this?
Yeah, there are many studies of gravitational lensing in the Gauss-Bonnet formalism. It's an alternative way of deriving the deflection angle. Sometimes I've seen those papers, but I don't remember the answer exactly. So if they actually describe also gravitational lensing in strong deflection limit in an easy way, I mean, because of course you have a different formalism. I think so, but I'm not sure about that. I would give you a wrong answer probably if
No
I
problem.
try.
No problem. Thank you. Thank you very much. Yeah.
Are there other questions? Maybe I can ask a question. To which spin is basically the strong lensing formalism valid? I know that there are actually some problems may occur when you go close to the extremal value. I mean, of course, the horizons coincide, and you have the photon orbits also coinciding in the Boyer-Lindquist coordinates with the horizon in some cases. Are there any
You
problems, or can you
mean
still apply?
so going back to, you mean in the extremal case of Kerr, you speak. Okay, in the extremal
Yes.
case, going into the extremal cases, so this study here was done without a strong deflection limit approximation, let's say. So it was done with a fully numerical code, actually, in order to obtain these pictures like this. Because analytically, we were able to obtain only an expansion for the low spins to the second order. Well, if you want to really go up to extremal Kerr black holes, for what I know, you have to go that you have to do that numerically. But one thing I would always like to do is to try an expansion of co-rotating photons around in the strong deflection limit in an extremal Kerr black hole, because in that case, a funny thing that happens if you look at the shadow flattens. So the fact that the shadow flattens, here you can see that the shadow flattens in the case of extremal Kerr black hole, it depends on the fact that the unstable circular orbit collapses to the horizon. So they coincide, okay? And in this case, of course, the logarithmic divergence changes. So you don't have a logarithmic divergence in this case. I think it's a divergence of 1/r, but I'm not sure that it has ever been explored. Okay, so this is one of the things I always say. I have to look into that. I've never looked at it. But as you see, there are many things that people that could be done in this. Also, in this case, extremal Kerr black hole. And concerning the gravitational lensing in the strong deflection limit, always holds. If you have a photon sphere or let's say an unstable circular orbit, even if there is no horizon anymore, okay? So even for example, if you pass the extremal Reissner Nostrum or even extremal Kerr black hole, and you have no horizon anymore, you have naked singularity. For some time you still have an unstable circular orbit, even if you have no horizon below. And in this case, you can still do a gravitational lensing in the strong deflection limit using that circular orbit as the basis for an expansion in the strong deflection limit. So it's still possible, even in that case. I don't know if this answers your question. If you have a different question.
To some degree, it answers it. Yes, thank you. Are there any other questions? Okay. If not, I would suggest we end kind of the official part here. Thank you very much again. I stopped the recording.